Hello, my name is Ato, and today I'm here to tell you about how you can think in very high levels about modern AI and sort of reason about systems like DALL-E 2, ChatGPT, large language models, and sort of learn how to apply them in your own ventures or, job or settings so that you can both reason about them without going into too much of the details of the weeds. Okay, so the aim I really want to get through at the end of this presentation is how do you reason about AI like Lego blocks, where you sort of know, what the block does, but you don't really know what's happening inside of that block. Another similar analogy is sort of how you can build a PC without really understanding what each of the components does, and that's sort of the aim that I want to get by the end of this presentation. So, a little bit about the motivations of why I'm doing this. I think, there's a funny thing in modern AI where it's like, if you're not in a big AI, like DeepMind, Anthropic, OpenAI, Stability, or Adept, you might as well just forget it. Because AI is very expensive, both in terms of data and compute. And so, you need to be quite like a PhD to sort of leverage the power of like modern AI. I think there's a lot of incremental progress in AI, but it's very, very difficult because there's a lot of technical terms, and sort of if you're not in the circle, it's very difficult to understand what's really going on. And lastly, I think there's way too much complex math for saying stuff that's relatively simple. So here's sort of the brief outline of what I'm going to be talking about. I'm going to sort of teach machine learning in a slightly different way to the way that a lot of courses would teach it. I'm going to teach it in terms of encoders and loss functions and sort of just generalize everything in under this framework. And then sort of later on, we'll learn about representations and then reason with those to talk about DALL-E 2 and how it works, as well as ChatGPT, and talk a little bit about reinforcement learning. And then finally, I'll just briefly touch on where I think there's a lot of really cool opportunities for both building companies, but also for doing research in the AI field. So let's get started. So let me just talk briefly about neural networks. This architecture has been the foundation of all of the phenomenal breakthroughs in AI since 2013. What it really is you just have a bunch of points, like you see here, and you just fit a very nice curve to it that sort of interpolates each of the points pretty nicely, and then the idea is that you would have generalizable ability even outside of the data set. So let's talk about encoders. So what's an encoder? Well, an encoder just takes a piece of data, and your piece of data could be a photo, it could be a sequence of text, or it could be a social graph that sort of shows all the relationships between your friends, your family, and then just maps it into a vector, okay? And, there's different encoders for different types of data, but the main idea is it just turns it into a vector of numbers, right? Which is this thing here. And, the key here is that the embeddings contain some useful information that you care about, and that useful information depends on what loss function you pair it up with. Here are some of the important questions to ask about encoders, which is like reproducibility, its ability to distill information, and its ability to capture spatial properties. There's obviously a lot more, but these are sort of the starting points that I want you to start thinking about. Now, I will sort of be using these words kind of interchangeably, so I'll kind of say embedding, hidden representation, latent representation. They all mean the same thing. It's just that vector thing that you saw the image get mapped to or the text get mapped to and stuff like that. So you have a bunch of different types of encoders. You have some of this stuff, which is like a CNN. Then you have a bunch of traditional RNNs where it's for text. You have some graph neural networks that sort of take a graph and then, pass on some of the messages. But you can ignore all of these details because these won't be necessary for sort of understanding how models work on a very, very high level. One reason why you should kind of care about the ability to encode stuff is composability for one. So, you can just like you can have two images, of like a gorilla and a axe or something, and you can say, well, you can encode it into a vector and just like put it together in a longer vector, and you can say, well, this is like a representation of these two things as a function, which is like a very basic use case of it. Here's a bit more of an involved use case, which is like, okay, so what word2vec does is it will take a word, right? So it can take a cat, kitten, dog, whatever, and it will map it into a vector. These vectors are just horizontal, but they're sort of all of these. And these vectors will have a spatial property where their sort of location in like a high dimensional space corresponds to sort of how similar they are. So, in other words, two things that are very similar, like a cat or a kitten, will be closer together. Whereas a house is a bit more different than cat, kitten, or dog, so it'll be further. But what's even more cool about Word2Vec is that you can do maths with these embeddings, right? So this is like one of the cool use cases about the embedding, which is now you've encoded this spatial dimension to like things that you wouldn't usually be able to apply maths on. So for example, here it's like you can see that man and woman are like sort of further away in this axis, and so is king and queen. And now what you can do is, well, you can do maths where you say, okay, a king minus a man plus a woman is a queen, right? And sort of it, and this makes sense because a queen, right, is a woman, uh, who has properties similar to a king, but you take away the male part, right? This sort of makes sense in an intuitive way. And what this can do is you can just make a mapping of sort of a bunch of different abstract concepts, and the Word2Vec model can sort of map all of these embeddings in different spaces so that you can see what their relationships are, how closely they're clustered together, and see all of the relationships between each of the words. And of course, you can replace these words with something else. It could be images. It doesn't really matter. So now let's talk about loss functions, which remember, the encoders, they learn some useful information about the original image, whether it be the image, the text, the social graph, and then the loss functions are what really helps the encoders learn what is important. So before I talk about loss functions, let me just talk about, the rough three types of tasks that exist in machine learning. So one is regression, where you sort of just try and predict a number, right, given the input data. So this is like a graph of a molecule, and maybe you want to work out the solubility of that particular molecule. Here, you want to sort of talk about is this image a cat or a dog, or it could be like a cat, dog, leopard, turtle, whatever. And then you have more nuanced prediction tasks where it's like structured prediction, where maybe you have an image and you want to sort of label which pixels are the cat and which pixels are the foreground and the background. Okay, so let's take it step by step. We'll talk about regression, which is, mapping from a data to a number. Okay, so now what you can do is, taking the exact same sort of encoder architecture that we had earlier. So, we have these encoders. It will take an image, let's say, turn it into vector, sentence into a vector, etc. And then what you can do is to each of them, you can attach a regression head. These regression heads are kind of like just different regression heads for different applications. And then these regression heads will predict the desirability and the price of that underlying data. And let me talk about, how we get to that and why this makes sense. Oh, and yeah, similar things for like, the importance of the text, or maybe predicting the political tension of the social graph. Okay, so when you're training a machine learning model, the most critical thing is the data that you have. So let's say, for example, you have a data set which consists of some NFTs, or like, I don't know, some art or something. It can be really anything. And then you also, for each of these, you have a corresponding desirability as well as the price. And you want to make a machine learning model where, given the input data, you want to be able to predict some number property about that particular thing. And so what you do when you're training these models is, okay, well, you go through each of the data points in the training set, and you will take the image, you'll encode it, and you get a vector, and then you get the regression head, and you predict the desirability and the price. And now what you do is, well, you look at the actual data, y, right? So that's this stuff here, and you just compare it with the results that your model predicted versus the actual results. And then what you do is you just take 4.7, you just take the difference of these two, you just take the difference of these two and square them together and add them together across each of the data, and that's your loss function, L. And then what you do is, these regression heads and encoders, well, they're composed of a bunch of numbers. It's just a matrix of just floating point numbers, and you would just you basically run this process called backpropagation, where you adjust these weights in the regression head as well as the encoder, and you basically minimize the loss. So you minimize how wrong the model's predictions are, right? And this makes sense because you're sort of taking away the differences between the actual value and the predicted value, and then just squaring them just so you get no directionality. And L you can think of as the loss is kind of like how wrong the model is. And you try and minimize how wrong the model is by minimizing the loss. So what's backpropagation, which is the process that we used here to train train the model, both the encoder and the regression head? Well, backpropagation is this algorithm that allows you to basically, given two parameters, right? Let's say theta 0 and theta 1. Well, it will kind of tell you the best combination of these weights, theta 0 and theta 1, such that you get the lowest loss, right? So this j of theta 0, theta 1 is the loss. And your loss is minimized here for I don't know, 0.8 and 0.4. And it can help you get that iteratively by sort of climbing down this loss, right? So you wouldn't actually see this, crazy heat map thing, surface thing, but this is sort of what's happening in abstract, where the algorithm figures out, at each step, okay, which direction should it go to? How should it adjust the weights such that you can keep minimizing the loss at each point. So, in this example, your model could be as simple as y dash is just theta 1x plus theta 0, and and your loss, right, is going to be this. So it's just going to be you take all of the data points, which are these red points, and then this is the predicted value, right, that this model gives, and you just take the differences between the data points and the predicted value, and depending on the different values chosen for theta 1 and theta 0, you'll have this kind of surface, and you want to choose the exact combination of theta 0 and theta 1 such that your loss is minimized as much as possible. And this sort of extends to models with thousands, if not millions, if not billions of weights. So billions of theta 1s and theta 0s. So imagine this process, but just very, very, very high dimensional. And so yeah, that's how you sort of build a trained encoder and a regression head, where you take an image, map it to a vector, get a regression head, and predict the desirability and price. Of course, you can do it for a bunch of other things as well. And this is how it learns through backpropagation. Okay, so now that we learned regression, let's sort of go over reconstruction and structured prediction, which works in a very, very similar way. You just take a slightly different approach with the loss function. So in this case, let's do reconstruction first. So in reconstruction, our data set is going to consist of just x is the original image, and the y is just going to be like the image itself. So what you're trying to do here, I know it seems a little weird, is you want to take the image, embed it into some vector, and then recreate the image once again. So, you know, what we want to do is we want to train decoders, right? So what we want to be able to do is we want to take the image, map it to a vector, and decode it back, and you get a slightly wonky, slightly different version of the original image, but you get the original image back. And what this allows you to do, right, is it allows you to encode what is essential about the original image in this vector, such that the model can learn how to, take that essence and reconstruct the original thing back. And so what we really care about is actually the decoder, because the decoder learns, how to take this embedding and create images. And you can already see how this is useful, where you can take a vector and you can use this decoder to create something, and you can sort of see how you would do like generative AI with like the cool DALL-E stuff, for example. Again, this is sort of a teaser towards that, but you can go from a vector into an image, and this is how we sort of create a lot of cool images. And yeah, the loss function that we use here is the reconstruction loss. So what's reconstruction loss? Well, what you do is you have the original image and the reconstructed image, right? Which is like the output of the model or output from the decoder. And you just like, take each pixel and you sort of subtract the values of it and see like, okay, what values of the pixels have changed. And you just like add all of that up, right? And just take the magnitude of it, and take the sum in a very similar way to the regression. You can kind of think of it as it's regression. This is a regression task where you need to try and predict every single pixel value as like one number to predict. And then this is kind of the setup. So you have the image, you have the encoder, that's the same as every other thing. But then what you do is you take a decoder and you try and reconstruct the image, and then you compare it. Again, remember x and y were the same in our case. You take the reconstruction loss, which is how wrong your model is, and then you just try and minimize the loss or how wrong the model is through the process of backpropagation that we explained earlier, where you try and climb down the hill. Which is this thing here. Now, one really cool thing that you can do is, as I alluded to, is you can create models that can like really that can generate images that you want, right? So this is an example of variational autoencoders, where basically, after you've trained it, you can take a random point in a vector field. Okay, so like, if you go back to the setup, well, you can just pick some vector, right? I don't know how big the vector is, often it's like powers, the vector size is like often a power of 2. You can just take a random spot in this space, and then the decoder from the variational autoencoder setup will basically decode that random vector into an appropriate image. And this is sort of like a mapping of, the different clusters and what they decode to using the decoder from the variational autoencoder. This one is for the digits, and this one's for a different set of data, which is on like different pieces of clothing, so shirts, shoes, trousers, stuff like that. But the point is, you can now go from the space of just random vectors to a space of images, and that's really the power of decoders and stuff like that. And so, yeah, just to recap, your model can basically take an image, remake it, but then the decoder can be used to generate a lot of images, which is really cool. Cool. And then there's sort of a very similar direction that you can take with something like this, where you can do semantic segmentation. This is more of a case where, you basically want to recreate the image, but you want to sort of decide what each value of the pixel is, and you want to basically classify different things in the image. For example, in this example, you kind of take an image, maybe let's say from a self-driving car, and you want to sort of say, okay, this thing is the vehicle, this thing is the road, and stuff like that. Similar thing here. And then it's also useful in like brain MRI scans, where you can sort of detect maybe tumorous regions or regions that the doctor should maybe pay more attention to. And the data set will look like X is the original image, and Y is the modified version of that image with different pixels having like different values or different colors. And finally, we have the classification task, where basically you would take the original data, you would have an encoder, as always, encode it into a vector, and then attach a classification head to it, and it will predict something about the original data. So you might predict if the original image is a cat or a dog. You might try and do the sentence completion. So if your sentence is like Sam Altman will rule the world with X, it will try and predict what the next best word is. And in fact, this is actually largely how a lot of these large language models work. They just try and predict the probability on the right-hand side. Or, you might take a social graph and see, is this social graph consisting of more left-wing or right-wing groups, for example. But there are obviously many different examples that you can take there. So in this case, your data set would look like this, where, like, for example, you'd have a piece of clothing, and then you would sort of try and your Y would be just like different probability distributions of like, what this thing is. So for this one, for example, it's 100% an ankle boot. So your data Y would kind of look like 100% for ankle boot, 0% for sneakers, 0% for sandals, and all the other classes of image types. And you would have that for each corresponding image here in the dataset. And it's not always the case that, like in this case, like you have 100% and 0% everywhere else, because, well, if you, for example, take the English language, well, you have you don't just have one correct answer when it comes to like the classification. So if you have an English sentence that starts with she said, comma, quote, I never, then like, and you want to predict the probability of the next word, well, these might be the most likely words that follows like this sequence of words. So it could be like, I never thought, I never knew, I never had, blah, blah, blah. And it will have different probabilities associated with the next word. And yeah, again, very similar things with like this sentence as well. And this is sort of how all of these large language models work. They just predict the probability distribution for what they think the next token should be. So how do you carry out the training? Well, it's very similar to the regression, since the regression end and the classification end, they look very similar, and they are. And what you do is you just you have like your data your classification head will predict sort of what's the probability that it's a cat, what's the probability that it's a dog, and then you'd compare it with the actual Y, and then you would apply this thing called a cross-entropy loss, which is this thing over here. Again, don't focus on what this actually means. It's just the choice of loss function used, and then you would calculate this as this loss, and you would use the backpropagation algorithm to optimize the weights in the classification head and the encoder such that you would get the optimal result and increase its predictive capacity, right? So that it's more right than wrong most of the time. And yeah, this is sort of just the ending. So like, again, you would be able to train these types of models that can take, whatever kind of data as an input, encode it into a vector, and then after attaching a classification head, it will be able to predict whatever the hell you want in your output data. So to summarize, yeah, we covered regression, classification, and structured prediction, which are like very cool tasks, and there's a lot that you can do with all of this stuff. Since you can take any piece of data, whether it be images, graphs, or text, and just like encode it into something, and depending on what you attach to the encoder, is you can predict various different things. But as you may have seen, no matter what task you're doing, you embed the input piece of data into some representation before you attach something that gives it the predictive capability. So for the regression head, for regression, it was the regression head. For classification, it was the classification head. And for structure prediction, it was the decoder that you train. And so all of these are the same. And sort of, I want to give this idea that, in a very abstract way, all of these tasks are kind of doing the same thing, just with different loss functions. And let me talk about operations on representations, which is sort of another reason why I wanted to teach machine learning this way, because these operations can really help you do some meaningful things with these encoders. So I've already given you the example about word2vec, where you can use these representations to do like math with things that you wouldn't be able to, and sort of you put like a notion of distance and like location to each of these concepts. There's another thing that you can do by turning it into a vector, which is taking the cosine similarity, or just really similarity. So what cosine similarity is in maths is, you have two vectors, right? Which are just like pointing in a very particular direction. And, cosine similarity basically just gives you the angle between the two vectors. And why that's important is because that angle tells you how similar those two vectors are. So if they are very similar vectors, you will have a very small cosine similarity because, well, the angles between the two will be very, very close. Whereas if they're orthogonal, they'll be quite different. And if they're opposite, well, man, they are really fucking different. And you can kind of calculate it using this formula. It's very, very computationally cheap and easy to do. And yeah, like here is just an example where like, each direction basically tells you like what you have in your sentence. And you can take cosine similarities between two different words. But this concept is very, very powerful because what you can do with cosine similarity is like, you can embed your piece of image, let's say, piece of data, let's say an image, right? And you can just kind of see how similar those images are, right? So, you can take an image of a dog and another dog, embed it into a vector, and you can take the cosine similarity between the two, and now voila, well, you now have this notion of like, okay, how closely related are they, or how different are they? And yeah, this is just like another example of doing different axes. Again, don't focus on the details, but the concept is all about, how to check for the similarity between different vectors. Okay, another reason why this is really, really useful, right? Applying that concept of cosine similarity is, well, let's say, you want to do a voice search, right? So let's say you have a database which, has like different audio, and you give it an input with this audio query. I might be like, hey, Alexa, like turn the play Despacito, right? And then I would have a encoder that would embed it into a vector or a hidden representation, which is this. And then what I would do is in the database, right, of all the different like instructions that you can give Alexa, well, the database will just like embed all of the different segments into a hidden representation as well. And then using the cosine similarity between this and the others, you can do nearest neighbor search, where you kind of say, okay, which vector is my vector, which is like a representation of my query, the most similar to, and then it can sort of guess which part or which audio data in the database that it is the most closely related to, and it allows you to carry out audio search. Another thing you can do is, well, if you have a piece of, let's say you have like a scene, right? Then, you can take one segment of it, maybe, or you can maybe take a product, get an encoder, and you get a vector now as an output of the encoder, and you can put that vector in like this massive vector space where each of the points just represent like a representation of something in the real world that is given by the encoder. And then what you can do now is, well, you can take the cosine similarity of that particular thing in images, for example, and you can say, well, have you seen this thing in like anywhere in this image, for example, or sort of find things that are visually similar. So, if you want to find a product that is very similar to this, right? You would encode it into a vector, and you would just say, okay, well, can I take the cosine similarity? Sorry, can I explore the vector space that is around that vector and find things that are kind of similar to this, and this is how sort of Google search could work, where you can take an image and sort of you say, can you find me something very similar to this? Now, I've covered the basics of machine learning, and this is sort of the part one. Now I'm going to be sort of talking about DALL-E, ChatGPT, and other parts of AI, which I think are cool, and that will be in the second video. So thank you for listening, and this was the intro part to machine learning and why you should think about machine learning in terms of encoders, why they're useful, why you should care.